In this video, we're going to begin developing a semantic model for our data. The very first thing we need to do is to identify the entities within our domain. So let's get to it. The most foundational entity in our model is the user story. A user story describes what a user does or needs to do to achieve some goal or objective. It captures the who, what, and why of a functional requirement. Developers work on user stories during sprints. A sprint is a set period of time during which a specific body of work, defined as a collection of user stories, has to be completed and made ready for review. So a sprint contains user stories. Sprints belong to some project. Completed stories are delivered to users in some release. User stories may be decomposed into a collection of tasks and aggregated into epics. A bug is similar to a user story in the sense that it may be decomposed into a collection of tasks and aggregated into epics, but that's where the similarity ends. Whereas a user story describes a functional requirement that must be satisfied, a bug describes a defect. The arrows represent relationships between the objects in our domain. We're going to discuss object relationships in more detail in another video, so let's hide them for now. There's one more entity that we need to add to our model. An issue is something that must be addressed through the work of an individual or a group of people. Epics, bugs, user stories, and tasks are specific kinds of issues. Notice that we have drawn the arrows here in a style different from the object relationships. That's because the nature of the relationship is different. In this case, we're defining a class relationship, not an object relationship. We can highlight the difference with a Venn diagram. In semantic modeling and in object-oriented programming, each type of entity is called a class. It is the set of all individual things of a given type. An arrow with a hollow arrowhead means that one class is a subclass of another. We can display that relationship in a Venn diagram by showing one class as a subset of another, like this. Now, suppose we have an epic E1, which contains user stories S1 and S2. Notice that we draw the containment relationships between elements within the sets. By contrast, subclass relationships are relationships between the sets themselves, not the elements within the sets. Okay, now let's go back to our other diagram. This is an example of a UML class diagram. It's a great way for humans to immediately grasp the entities within a domain, but it's not so good for machines. If we want computers to manipulate the entities, we need to describe the classes in a language that computers can easily parse. That's where the web ontology language comes in handy. It's more commonly known as OWL, which comes from the first letter of each word with the W and O transposed. The folks who invented the web ontology language decided that OWL was catchier than WAL, especially since owls are associated with wisdom. An ontology is a formal inventory of the classes, properties, and relationships that exist in some domain. Here's how one might express the classes in our domain using the web ontology language. Let's break this down. The first line declares a namespace for our classes. This namespace is effectively an identifier for our ontology. We define a prefix so that we can refer to the elements within our ontology using a shorthand notation. PMD stands for Project Management and Delivery. Notice that this prefix appears in front of the names of all of the classes within our ontology. A name with a prefix in front is called a compact URI, or curry for short. To produce the fully qualified name for a class, simply replace the prefix with the corresponding namespace URI. There are several different file formats for expressing semantic information. We're using the so-called turtle format. In this syntax, fully qualified names appear inside angle brackets. but the compact URI notation is less verbose and tends to be more readable, so we'll stick with that. Namespaces are useful for two reasons. First, they allow us to disambiguate different senses of a word or phrase. We're using the word bug to mean software defect. Someone else might use the word to refer to an insect. Because we're using URIs to name the terms in our ontology, we avoid possible confusion with other senses of the same term. By definition, every reference to the class at this address is a reference to a software defect, not an insect. The second benefit is that anyone can dereference the URI to get more information about the term and how it is used. We're using a fictitious domain, example.com. When creating a semantic model for real, you should use an actual internet domain and publish information about your ontology at the address that you choose. The second line declares a namespace prefix for the OWL vocabulary. We use this vocabulary to specify the classes within our ontology. Let's take a closer look at one of those class definitions. This line declares that an epic is an entity type. In other words, epic is a class within our ontology. The next line states that an epic is a special kind of issue. We say it is a subclass of issue. The rest of the class definitions are similar. When designing an ontology, you could use a plain text editor to author a file like the one you see here, but most people use a specialized editor. The World Wide Web Consortium maintains a list of ontology editors. You can certainly use one of these editors, but we think the easiest way to build an ontology is to put your terms into a spreadsheet and let the Koenig toolkit generate the OWL definitions for you. In the next video, I'll show you how to do that.